Hey physicists, what's crack? So today we're going to do some thermal physics. So what it says is we've got 11 gram of ice and we're dropping a bucket and we're trying to figure out what the equilibrium temperature is reached, okay? So first thing, just draw pictures because it always helps you imagine it. So we've got a bucket and it says, again, we've got 0.7 kilograms of water and that water is at 25 degrees Celsius. And then what we're doing is we're dropping that ice that is 11 grams. So just remember the first thing you got to do is put that into kilograms. So it's going to be my 0.011 kilograms of ice, and it's at -5 degrees Celsius. So you have to remember there's two things involved here. It's the specific heat capacity because there's a change in temperature, and the specific latent heat of fusion because there's going to be a change in state. And the clue is, how to do the math here, is if they give you all the numbers, you have to use them somewhere. Okay, so there must be a change in state, and then I must have a change in temperature for both the ice and the water. Okay. So first, my ice starts at -5, and you need to remember that ice changes state at 0 degrees Celsius. So the first thing that has to happen is my ice has to increase in temperature by 5 degrees Celsius. So that change in energy there will be my mass of my ice times the specific heat capacity of ice, which is 2,100, times by that change in temperature of the ice. And when I do that math there, I'm going to get a final answer of 105.5 joules. So once my ice now has increased in temperature to 0 degrees Celsius, I now have 11 grams of ice at 0 degrees Celsius. But that ice now has to change state, so it can be 0 degrees Celsius of water now. So now I've got to calculate the change in state. So my change in state is just M times L. So my mass of my ice times the specific latent heat of fusion of my ice, which is 3.36 times 10 to the power 5. And when you do that math, you get a final answer of, bear with, 3696. Okay, so now what we have, if we have water, this mass of water at 0 degrees Celsius, and we have this mass of water at 25 degrees Celsius. So both of those liquids now are going to come in thermal equilibrium with each other. So my ice that's now liquid water is going to increase in temperature from 0 degrees Celsius, and my bucket of water is going to decrease in temperature from 25. So the increase in temperature of my water that's now at 0 degrees Celsius is going to be the mass of the water that is at 0 degrees Celsius times the specific heat capacity of water, because we just said it's water at 0 degrees Celsius, times the change in temperature. And the change in temperature is going to be whatever the final is minus the initial. Because the initial is 0, we can just ignore that and just have it as T for our final temperature. And then for our water, we just said the water is going to drop in temperature. So the specific heat capacity equation we have to use, the change in energy there is our mass of water that is at the 25 degrees Celsius times the specific heat capacity of the water times the change in temperature of the water. And normally we'd write final minus initial, and the initial is 25. But because we know this water is going to drop in temperature, that's going to give me a negative number. But the change in temperature here always has to be a magnitude. It has to be positive. So you just need to remember for your math to work that you have to change that around TF minus T, because you pop your answer in there to get a positive magnitude. So when you solve this out, you're going to get a final number there of 73500 minus 2940T. Okay. So again, this is a drop in energy because my water dropped in temperature. This was an increase in energy because my ice had a rise in temperature to 0. That was an increase in temperature because my ice had to change state. And again, that was an increase in energy because my ice has to increase in temperature to become into that final equilibrium temperature. So now all we do is we have to equate the energy loss to the energy gain. So you just write out your final line of math, which is 115.5 plus 3696 plus 0.011 times 4200 times by T, and that's going to equal this line. So 73500 minus 2940T. And all you need to do is take your numbers to one side and your T's to one side. So I would probably take the number here over to become negative and take this one over here to become negative, and you get your final answer of an equilibrium temperature of 23.3 degrees Celsius. And again, it's in Celsius, not Kelvin, because I kept them in Celsius in these parts of my brackets. So that's grand.